Okay, so physiological physiological basis of herbicide selectivity. Herbicide selectivity. Now, our first question is how do herbicides enter the plants? Now, most herbicides enter the plants via leaves and probably stem and the roots. Okay, I should put a question mark here. So number one, we are going to talk about differential. In plants, differential movement of herbicides in plants. Here we want to specify the cuticle. This is a herbicide barrier. This prevents herbicide movement. So we have got the cuticle. If the herbicide cannot enter the cuticle, it means that herbicide is not going to kill that plant. Therefore, the cuticle can give protection to the plant, and this could be the basis for selectivity. Now let us consider young plants versus old plants. young plants could die because their cuticle is not fully developed, whereas the old plants will survive because the cuticle will prevent the movement of the herbicide. This is why we say that young plants are easily susceptible to herbicides, whereas old plants can actually resist these herbicides. So the herbicides, now let's suppose the herbicide has now entered the plant system. What is going to happen? Movement of the herbicide within the plant let us use example of 2,4-D. When this herbicide is applied, it is applied in the form of an ester. The reason is that the ester is able to pass through the cuticle. This improves entry of the herbicide into the plant. But this herbicide has to reach the site of action. If you formulate it as an ester, it can easily reach the it can easily enter the plant. However, you may note that if you have got a formulation of a salt, this herbicide may not easily enter the plant. So if it is in the form of a salt, like some other herbicides which can be in the form of salts, they cannot easily penetrate the cuticle and they cannot kill the plants. But the ester can easily go into the plant and kill it. But before it can kill the plant, it has to reach the site of action. It has to reach the site of action. So It is the amount of herbicide at the site of action that determine the fate of that plant. So 2,4-D is to be converted to an acid. Once it is in the 2,4-D acid form, then it can easily move within the plant. However, it is the rate of conversion from this form to that form rate of conversion which determine whether the plant is going to survive or not. If the rate of conversion is very high, it means there's going to be a lot of 2,4-D which is going to be moved to the site of action, and the plant is going to be killed. Now, in the plants where 2,4-D is moved slowly, like in grasses, the grasses are not going to be killed by 2,4-D, but the broadleaves plant which move a lot of 2,4-D very fast, because the conversion is very fast, they are going to die, because the herbicide can reach the site of action very quickly. We also have 2,4-D. It can kill soybean. But not sugarcane. The reason is that in soybean, the movement of 2,4-D is very fast compared to that of sugarcane. We also have an example of soybean with a chemical known as gall. Again, gall does not move very fast in soybean, and it may not kill soybean. Although in Zimbabwe we are not using gall for weed control in soybean. We also have an example of carrots. There's a herbicide called the linuron. This herbicide is not easily moved within carrots, but it can easily move within weeds. Therefore, we have selectivity. So the movement of the herbicide, once it has gone through the cuticle, may determine whether we are going to have a selectivity or not. And we can have good examples from 2,4-D, gore, and linuron. We have got what is known as compartmentalization, which can occur in plants. What this simply means is restriction, herbicide restriction. So the herbicide is kept in certain areas. And may not reach the site of action. Again, probably linuron in carrots could be the example, and also 2,4-D. Because there's a restriction in terms of movement, so these herbicides may not reach the site of action. Okay. The other one is sequestration. Although similar to compartmentalization, here we are referring to what can happen to paraquat sprayed to conizer. Arbida. Paraquat is restricted to areas away from the site of action. So you have a species of conizer which resist paraquat. So sequestration is a process where the herbicide is restricted in some plants, like Coniza rubida. We know paraquat kills everything which is green, but when it comes to Coniza, it is restricted in certain areas in such a way that it doesn't reach the site of action, and therefore Coniza is not killed. So it gives rise to selectivity. Number 4, I want to talk about altered site of action. Here we are interested in enzymes which have been altered. Probably for the herbicide to express its mode of action, it may need to bind to an enzyme. If I can use this model, herbicide A, B. If we look at situation A, we can find that the herbicide cannot fit. But this can fit. So what happens is that we have grasses and broad leaves. Now in grasses, we have herbicides which can perfectly fit to the enzymes, and the grasses will die. But In broadleaves, which is A, this is for broadleaves, this is for grasses. In broadleaves, the herbicide cannot match the enzyme. Therefore, the broadleaf is going to survive. We have herbicides which are known as grass killers. These grass killing herbicides form a perfect fit with enzymes within grasses, and they are able to express their mode of action by probably stopping fatty acid production, leading to the death of the grasses. But in broadleaves, the herbicide enzyme combination is not possible, so the broadleaf crops or plants are going to survive. In most crops like groundnuts, soybean, we can use grass killers. And this is the principle of the selectivity. I'll give you examples where altered site of action or where altered enzymes can result in selectivity. Number one, we've got triazines. Number two, we have got glyphosate. What you are saying is that selectivity can depend on the ability of the herbicides to bind to the enzyme, resulting in selectivity. Then we have what is called phenoxy propionates or phenoxy carboxylic acids, phenoxypropionates or phenoxycarboxylic acids. And cyclohexene dione, long names. The other ones are sulfonylurea, Nile, urea, and imidazolinones. So what we are saying is that within these families, the triazines, the glyphosate, allyloxyphenoxypropionates, or allyloxyphenoxycarboxylic acids, and cyclohexene-diones. Then we have got sulfonylurea and imidazolinones. These depend on enzymes for selectivity. Let me change the color because I want to start with the atrazine. Right. Now with atrazine, for atrazine to kill or triazine to kill a plant, there is what is known as a plastoquinone. Now, atrazine is to bind to this plastoquinone, express its mode of action, and kill the plant. But if the binding does not take place at the plastoquinone, then there's going to be selectivity. For glyphosate, there is what is called EPSPS site. I think it would be nice to just to know it as EPSPS for the moment, or just remember it as the EPSPS. Now, if glyphosate can bind to EPSPS, it can kill the plant. But if it cannot bind to it, then the plant survives. In in GMOs, where we have got maize and soybean, GMO, scientists have actually manipulated these maize and soybeans so that the EPSPS will not combine with the glyphosate, and we can produce selectivity. Now, with the allyloxyphenoxypropionates, we have an enzyme which I will just shorten it like this, ACC case. Acetyl coenzyme A carboxylase, and you can write it in short like this. So what it means is that for this group of herbicides, the allyloxyphenoxypropionates or allyloxyphenoxycarboxylic acid and the cyclohexenedione herbicides, they should be able to fit to this enzyme, acetyl coenzyme A carboxylase, for them to express their mode of action. But in grasses, this is where it can happen, and this group of herbicides can selectively kill grasses in groundnuts as well as soybeans, because of their ability to combine with the enzymes. But in the broadleaves, soybean and groundnuts, these herbicides are not going to combine with this enzyme. Therefore, the crop is going to survive. We have examples of herbicides like NAB, which is, I think, a cyclohexenedione. Then we have got the common one, fusilate. Which is an allyloxyphenoxypropionate. So these, they are very selective herbicides. These are some of them. Now, if we come to sulfonylurea and imidazolinones, I think they have this enzyme AL acetolactate synthase enzyme. Sometimes it is called, I think, AHAS, acetolactate synthase enzyme. These sulfonylurea and imidazolinones need to fit to these enzymes in order to express their mode of action, and it can be done in grasses. But I want to talk about a sulfonylurea herbicide which can also be used in maize, known as nicosulfuron. Although maize is a grass, it's not going to kill it, but it can kill grasses. Then on imidazolinones. Probably I can give an example of what is known as imazaquine, which can kill grasses, probably in soybean. There's also imazatapa, which is also a grass killer in groundnuts. So probably what you need to remember is that these herbicide families, the principle of selectivity is based on the enzyme. That is the issue here. So physiological basis of selectivity what we should know is that everything happens in the cells. A lot of biochemical reactions. We don't want to spend too much time going into the cellular activities, but this is where everything is taking place. So there is a differential penetration or movement. Herbicides penetrate faster in young weed seedlings than mature weeds. It's because of the cuticle thickness which increases with age. We've said ester formulations of 2,4-D can penetrate fast into the cuticle compared probably to the amine and other salt formulations. And this can partly account for the selectivity of foliar applied herbicides, the formulation of the herbicide. Soybean can tolerate oxyfluorophane gall because of the slow absorption of the herbicide. The movement is slow. Now, the response of sugarcane, which is tolerant, and the beans, which is susceptible to 2,4-D, again, it's due to the movement of 2,4-D. The speed at which this herbicide moves within the plant determine whether the plant is going to die or not. In the beans, the movement is very fast compared to sugarcane. It is the 2,4-D free acid which is translocated in the phloem to the site of action. So the speed of conversion from ester forms to acid forms is very critical. We call it de-esterification. From amine form to acid forms, it's deamination. So tolerant plant species have got processes of conversion which are very slow, or de-esterification or deamination. Well, that is the ester the chemical representation of an ester, which can split into an acid and an alcohol. Here we've got the 2,4-D methyl ester, which can be split into 2,4-D acid and alcohol. Please don't try to memorize these formulas. It's not important to memorize them. If we want you to know something, if we want us to if we want you to answer a few questions on these ones, we actually provide you with the formula. So don't worry about the complexity of those formulas. Compartmentalization, we said the herbicide is restricted in areas of the plant where no damage occurs. The herbicide will not reach the site of action. Examples are linuron, which is inactivated at the point of entry in carrots. Then 2,4-D and other phenoxy herbicides have got very slow rate of translocation in grasses. So they tend to be compartmentalized. It's like imprisoning some. It's like a prison, compartmentalization. If you are troublesome, they throw you into the jail, to restrict your activity. Sequestration. Herbicide is also kept remote from the site of action. Like paraquat is kept remote from the site of action, which is the chloroplast. The example is the conizer species. We know it's green. When we spray it with the paraquat, it will not die because of this issue of sequestration. It's selectivity, but it's not the selectivity which farmers want. So what can produce selectivity? It can be differential penetration across the cuticle, differential translocation movement within the plant. Also issues like compartmentalization and the sequestration can contribute to selectivity. Then we also have the altered binding site of action on the enzymes. The altered binding site of action, which I have tried to illustrate, where you have if atrazine cannot fit at the D1 protein, the plant will survive. You have a tolerant plant. If it fits nicely at the plastoquinone binding site, you have susceptible plants. So the herbicides which are affected by the altered binding site of action are the following groups: triazines, glyphosate, sulfonylureas and imidazolinones, allyloxy, phenoxy, carboxylic acids, or cyclohexindiones. Sometimes we shorten for allyloxy carboxylic acids, we just call them the FOPs, F-O-P-S. Cyclohexindiones, we just call them the DIMs, DIMS in short, if you don't want to memorize these things. So these herbicides bind to specific site of action or sequence of amino acids on the target enzyme molecule. For allyloxyphenoxycarboxylic acids, we have got differences in acetyl coenzyme A carboxylase or ACC case between broadleaves and grasses. Herbicides capable of binding to grass form of acetyl coenzyme A can disrupt lipid synthesis, while broadleaf species are not affected. Here are examples of allyloxyphenoxycarboxylic acids: fusilade or fusar-4-butyl, pilot super or quizalo-4-ethyl, holon or dichloro-4-methyl. You can choose the name which you can remember here. Probably it's easy to remember fusilade. Cyclone hexene dione herbicides, we have got NAB, cetoxidium or select clothianidin. These are used in broad-leaved crops. Differences in acetyl coenzyme A carboxylase in grasses and broadleaves, as we have said, will result in selectivity. For triazines, we have the altered quinone binding site, which can result in resistant weed biotypes which are not affected by triazines. So again, it may not be the type of selectivity which we want. Sulfonylurea and imidazolinone herbicides. We have got, this is now the correct, probably the abbreviation for acetolactate synthase, ALS. You add ASE there. A change in amino acid sequence on the enzyme can prevent binding of sulfonylurea and imidazolinone herbicides, or acetohydroxy synthase. Sulfonylurea herbicides, we have got chlorsulfuron, primsulfuron, but nicosulfuron is easy to remember because it is commonly used in maize to kill chamfer grass. It's known as accent. Imidazolinone, we have got imazapa, imazamox links in groundnuts, or imazatapa pesut in soybeans. I indicated there could be also imazaquin. Glyphosate can inhibit 5-enolpyruvyl shikimate 3-phosphate synthase, EPSPS. Maybe just call it EPSPS. It will solve a lot of our problems. The altered EPSPS imparts glyphosate selectivity in GMO maize and soybeans. So the type of selectivity which is physiological, which have been discussing, It concerns herbicide mobility. It can also concern the herbicide binding at the enzymes. So this is it for the enzymes and the herbicides mobility. Let me stop here.